Right, let's look at an example of a colligative property calculation. And what we're looking at here is a freezing point, calculating freezing point, and we're looking at calculating the freezing point of the phenol and acetic acid solution we were looking at earlier. And that would be this one back over here. And you'll remember that we had calculated different concentration quantities based on the data that we were given in the problem. So 22 grams of phenol and 160 grams of acetic acid. Now again, we're looking at this same solution, and we're going to be able to calculate how much a freezing point gets depressed by, how much a boiling point gets increased by, and the vapor pressure lowering and the osmotic pressure. Alright, so how we do that is we use these kinds of formulas. The first one is the delta TF equals KFM formula, which tells us the change in freezing point. KF is called the mole freezing constant, and that's a unique value that depends on the solvent, and it's going to be a constant value. You'd have to be given that value under normal circumstances. The KF of acetic acid is 3.90 degrees Celsius per mole, or if you'd like, per degrees Celsius kilograms per mole. Now the formula is the KF multiplied by the molality, and you'll remember we got the molality, we calculated it back over here, molality of phenol, and that was going to be 1.4 molal, or moles per kilogram. That's where I got the 1.4 from. So it's going to be 3.90 degrees Celsius per molal times 1.4 molal. You see the molals, or the moles per kilogram, will end up cancelling, and you'll be left with degrees Celsius. So the change in freezing point is 5.5 degrees Celsius. Now from the discussion I had earlier, you'll see that it's always freezing point depression, so we know the freezing point always goes down. We are given the freezing point of pure acetic acid as being 16.6 degrees Celsius. So we know that after we've put 22 grams of phenol into that solution, it's going to go down by 5.5 degrees Celsius. And that means that the new freezing point will be 16.6 degrees Celsius minus 5.5 degrees Celsius, which is 11.1 degrees Celsius. The minus here is because it's always freezing point depression. Boiling point can be calculated by using a similar formula. We use the molal boiling constant, which is usually different to the molal freezing constant. Again, it's unique to different solvents, and you'd have to be given that value. And for acetic acid, it's 3.07 degrees Celsius per molal. The change in boiling point then can be calculated by taking 3.07 degrees Celsius per molal and multiplying by the molality, the same molality as we used earlier. This comes out to be 4.3 degrees Celsius. Now remember, it's boiling point elevation, so what's going to happen is that the boiling point, which is given to us as being 118.0 degrees Celsius, that's the pure acetic acid, and when we add phenol to it, 1.4 molals worth, we're going to end up adding 4.3 degrees Celsius to the boiling point of acetic acid. So the new boiling point will be 118.0 plus 4.3 degrees Celsius, giving 122.3 degrees Celsius. Again, take a look at the significant figures. You can see that we're doing addition, so we are going to use the smallest number of decimal places. This is 1 decimal place and 1 decimal place, so the answer comes out to 1 decimal place as well. Next we can look at the vapor pressure, and vapor pressure is figured out using this particular formula. The change in vapor pressure of the solvent is decided by the mole fraction of the solute. Remember, this is all about solutes. This over here, there's the molality of the solute, and this here is the mole fraction of the solute, and we calculated that to be 0.079. I'll take that back to where we found that. There we go. And we found out the mole fraction of phenol was 0.079. Don't get mixed up and take the mole fraction of acetic acid. All that matters here, what's affecting the vapor pressure, is the mole fraction of the solute, which is phenol. And we do that, we take 0.079 times the vapor pressure of the pure solvent, which was given to us as being 20.0 torr at this particular temperature. The temperature is not used as part of the problem. All we're interested in is the vapor pressure at that particular temperature, which is 20.0 torr. The change in vapor pressure then will be 0.079 times 20.0, which is 1.6 torr. Now what we know is that vapor pressure is lowered because it's vapor pressure lowering, so the new vapor pressure will be the vapor pressure of the pure solvent, which is 20.0 torr minus 1.6 torr. And that will give us 18.4 torr as our new vapor pressure once we have that concentration of phenol added into our solution. Osmotic pressure is gotten by taking the molarity times R times T. The R value is the same R value as we use in gas calculations, and you can see it's pi equals mRT, where m is the molarity of the solution. We found the molarity of this solution to be 1.2 moles per litre. Take you back, there we go. Its molarity of phenol was 1.2 moles per litre, or 1.2 molar. And that's times 0.08206 litres atmospheres per mole per Kelvin, again a constant value that you'd have to be given, times the temperature, which is 298 K, 25 degrees Celsius, converted into Kelvin. We do this calculation, we come out to 29 atmospheres. So that's what that's how we can calculate the osmotic pressure. It's quite an appreciable amount, and it certainly adds to the notion that it's very difficult to take a solution like a salt solution, the seawater, and convert it into a pure solvent. The way that's done is by a process called reverse osmosis, where we end up putting pressure on the solution to try and push pure solvent back through the semipermeable membrane. That's a very difficult thing to do. We need at least 29 atmospheres of pressure to do that. It takes a lot of energy to create that kind of pressure. And seawater is no different. It also requires a very appreciable amount of pressure to convert salt water into pure water.